Hello chemists, here is another video. In the last video, we talked about going from molecular formula to percent composition by mass. So for example, going from H2O to what percent is hydrogen and what percent is oxygen in H2O. Now in this video, we're going to go from percent composition by mass to the empirical formula. So we'll go from the percent oxygen and the percent hydrogen and find what the empirical formula is. And then we're going to take one last step and find what the molecular formula is. As you remember from the last video, if the empirical formula of something, let's say, is CH, the molecular formula could be C2H2, C3H3, C6H6, so on and so forth. So we're going to use another piece of information after we get the empirical formula to find the molecular formula. And here is your roadmap for doing that. So you'll want to have this handy when you're doing these problems. You start with the percent composition by mass. You are given this. Okay, you're given this. Then you're going to convert to the moles of each element. How you do that is when you start with the percent composition by mass, you assume you have 100 grams of something. Okay? That way you can easily go from percent to grams. Okay? And you'll see how that works when we do the example problem. Okay? And then you're going to go right from grams to moles. So again, you go right from percent to grams. That's the first step. And then you're going to go from grams to moles. How do you convert from grams to moles? That's using the molar masses. Okay, so now you have the moles of each element. To get to the mole ratios of elements, you need to divide by the smallest number of moles. And that'll get you to the mole ratios. And then to go from the mole ratios to EF, which is my abbreviation for empirical formula, you need to change the subscripts to whole numbers. Okay, hopefully they will be really close to whole numbers. You'll see how that works. And then to go from the empirical formula to the molecular formula, that's going to involve one more step. Okay, you need to take the molar mass of the compound and divide by the empirical mass. Okay, now I need to give you the molar mass of the compound. That's a piece of information I give you. And the percent composition by mass is a piece of information that I give you. And then when you take the molar mass of the compound that I give you, divide by the empirical mass, which comes from adding up all the molar masses of your empirical formula, then that will give you around a whole number. Okay? And then you take that whole number, you multiply the empirical formula by that number, and that will get you to the molecular formula. Now I know this sounds complicated, so let's do an example using this roadmap. So here's our first example. An unknown compound is composed of 40% carbon, 6.72% hydrogen, and 53.29% oxygen. If the molar mass of the compound is 180 grams per mole, what is its molecular formula? So what is this unknown compound? Okay, so for the first step, okay, you're going to assume you have 100 grams. You're going to assume you have 100 grams of this unknown compound. Hopefully you understand that if you have 100 grams of the compound, or if you have 10 grams of the compound, or if you have 1 gram, it's still, the percentages of carbon, hydrogen, and oxygen are still the same. It's still going to be 40% of carbon, so on and so forth. So it doesn't actually matter how much of it you have, because the percentages, which are really ratios, are still the same. So we assume we have 100 grams because that makes our math really easy. If we have 40% carbon in this compound and we have 100 grams of this compound, then 40% of 100 is 40.00 grams of carbon. Now likewise, if we have 6.72% hydrogen, 6.72% of 100 is 6.72 grams of hydrogen. And likewise, we'll have 53.29 grams of oxygen. Okay? So now we've done the first step. We've converted from percents to grams. Now we need to go from grams to moles. Okay? So if we have grams on the top, we'll put it on the bottom, and we'll put moles on the top. What is the molar mass of carbon? It is 12.01 grams per 1 mole. How about hydrogen? 1 mole is 1.01 grams. And for oxygen, 1 mole is 16.00 grams. Now we'll do out the math for each of these. You'll take 40 and divide by 12.01. You'll take 6.72 and divide by 1.01. And you'll take 53.29 and divide by 16. Now what you should get is 3.331 moles of carbon, 6.65 moles of hydrogen, and 3.331 moles of oxygen. So now we have the moles of each element. And now we need to get to the mole ratios of the elements. And I told you to do that by dividing by the smallest number of moles. So in this scenario, we have 3.331 moles, 6.65 moles, and 3.331 moles. I think you understand the smallest number of moles we have there is 3.331. So we'll divide them all by 3.331 divided by 3.331 and divide that by 3.331. It's okay if the smallest one occurs twice. That's fine. Now I'm going to come down here. 3.331 divided by 3.331 for carbon would be 1 mole of carbon. 6.65 divided by 3.331 is 1.996 moles of hydrogen. And then for oxygen, 3.331 divided by 3.331 would be 1 mole of oxygen. So to write these as whole numbers, 1.996 is going to really be 2. Right, 1.996 is so close to 2 that we can round it to 2. So to get the mole ratios, we'll write these as subscripts. So we have 1 C, so we have the invisible 1 subscript, 2 H's, and 1 O. That is our empirical formula. I'm going to label that EF. That's our empirical formula. It's the simplest ratio of our carbons to hydrogens to oxygens. Okay? So again, these numbers that we have here as subscripts, invisible 1s and our 2s, represent the ratio of moles or atoms. In this case, we're talking about moles. 1 mole of carbon, 2 moles of hydrogen, and 1 mole of oxygen. But these, because it's our simplest ratio, it's our empirical formula, we can't say that our molecular formula is necessarily CH2O. It could be, but it could also be C2H4O2. It could be C3H6O3. There's many options here. So that's our empirical formula, but we need to figure out now our molecular formula. How we're going to do that is we're going to take the molar mass of the compound and divide it by the empirical mass. So let's take the molar mass of the compound, which I give you. Notice that it's up here. I give that to you, 180 grams per mole. So we'll take 180 grams per mole and divide that by the empirical mass. The empirical mass is the molar mass of your empirical formula. So we need to add up the molar mass of our empirical formula. So 1 carbon, 2 hydrogens, and 1 oxygen. What's the molar mass of that? And you should get that it's 30.03 grams per mole. That's the molar mass from our empirical formula. So I take 180 grams per mole, divide it by 30.03 grams per mole, and I should get something close to a whole number, and I get something around 6. Okay? I get something around 6. So that is our factor. What we need to do is we need to take the empirical formula and multiply it by 6. And that should give us C6H12O6. And that is our molecular formula. And hopefully you know that C6H12O6 is glucose. Glucose has an empirical formula of CH2O. So first we found that empirical formula, and then by taking the molar mass of the compound, which I gave you in the problem, and divide by the empirical molar mass, which we get adding it up on the periodic table from the empirical formula, we get a factor of 6. We take this empirical formula, we multiply every element in there by 6, and we'll get the molecular formula, C6H12O6. A lot of steps, but they should make sense and be logical. Chemists, here is your next example. It has to do with smog, and smog, if you don't know, is a type of air pollution common in cities because of emissions from vehicles and industries. Not good. So smog is 19.8% carbon, 2.50% hydrogen, 11.6% nitrogen, and the rest is oxygen. If the molar mass of smog is 120 grams per mole, find the molecular formula of smog. Okay, so we have the percents of everything but oxygen. Okay, so the first step is going to figure out how much is oxygen. How I would do that is to add up 19.8% carbon, 2.50% hydrogen, 11.6% nitrogen, and that way you can figure out, when you add those up and subtract them from 100, how much is oxygen. So if you do that now, you should get that your percent oxygen is 66.1%. So we have 66.1% oxygen. Again, how I did that is I took 19.8% carbon, I added 2.50 and 11.6, and then I subtracted from 100. Because all of your percents should add up to 100. So I subtracted from 100, and I get 66.1% oxygen. So now the next step is to take the percents and convert them to grams. Remember that if we assume we have 100 grams of smog, then it's really easy because you can convert right from percent and just say you have that many grams. So let's say we have then 19.8 grams of carbon, 2.50 grams of hydrogen, 11.6 grams of nitrogen, and 66.1 grams of oxygen. Okay? Now that we're in grams, the key always in chemistry is to go from grams to moles. So now convert each of them from grams to moles. Okay, pause it now to give yourself a second to do that. So here is what I got. I took 19.8 grams of carbon, divided it by its molar mass, which is 12.01, and I got 1.65 moles of carbon. I then took 2.50 grams of hydrogen, divided it by its molar mass, which is 1.01, and I got 2.48 moles of hydrogen. I then took 11.6 grams of nitrogen, divided it by its molar mass, which is 14.01, and I get 0.828 moles of nitrogen. Then I took 66.1 grams of oxygen, divided it by its molar mass, which is 16.00 grams, and I get 4.13 moles of oxygen. So the next step is to go to mole ratios. Okay? You need to get to mole ratios. The best way to do that is to divide by the smallest number of moles. So I'm going to take these and figure out which one's the smallest. Okay, 0.828 is the smallest. So I'm going to divide all of these by 0.828. Divide that by 0.828. Divide each of these by 0.828. Sorry, I'm running out of space. Okay, so 1.65 divided by 0.828 should give me a number pretty close to 2. 2.48 divided by 0.828 should give me a number pretty close to 3. 0.828 divided by 0.828 is 1, and 4.13 divided by 0.828 should give me a number pretty close to 5. Okay, so if I have 2 carbons, 3 hydrogens, 1 nitrogen, and 5 O's, how I can write that is C2H3NO5. And that is our empirical formula. So the next step after we have our empirical formula is to write the molecular formula. And again, how we do that is we take the molar mass of the compound and divide by the empirical molar mass. The molar mass of the compound, I tell you up here, is 120 grams per mole. So you'll take 120 grams per mole and divide it by the empirical molar mass. Again, you get the empirical molar mass from the empirical formula. So add up 2 carbons at 12.01 each, 3 hydrogens, 1 nitrogen, and 5 oxygens, and you should get 121.06 grams per mole. Okay, so we take 120 grams per mole, that's the molar mass of the compound, divide by the molar mass from the empirical formula, 121.06 grams per mole, and you should get something close to a whole number. In this case, we get something really close to 1. So then what you do is you take this empirical formula and you multiply it by 1. Every element in that empirical formula by 1, so you get the same thing. You get C2H3NO5. So that's also our molecular formula. And as we saw in the last video, like H2O, for water, H2O, the empirical formula and the molecular formula are the same thing. Well, in this case, C2H3NO5 is the empirical formula, and it's also the molecular formula. These problems will take a lot of practice, and because there's so many steps, and we'll make sure that you get a lot of practice. Nice job today.